Hey, my name is Goksel and this is my Cmpe 491 project for this semester, verification of multithreaded software using bounded model checking and Llvm framework instructed by Alper. Processors started to shift from single-core architectures to multi-core architectures. However, developers still find it hard to write multithreaded software that can exploit these multi-core architectures compared to sequential ones. Some of the problems are deadlocks, mutual exclusions, and race conditions. Formal verification proves correctness of programs. Exponential number of behaviors resulting from threaded schedulings, and this makes verification a very challenging problem for multi-threaded programs. Software testing cannot always find concurrency bugs, whereas formal verification can prove programs' correctness and gives 100% coverage. And now, some insight for the important concepts in my project. Idea of bounded model checking is searching for a counterexample in the given problem until a finite execution length n. The bounded model checking problem can be efficiently reduced to SAT or SMT formulas, and they can be solved by very efficient solvers. Llvm is a compiler infrastructure supports a language-independent instruction set and type system. We can verify concurrent programs in languages that Llvm supports, which include C, C++, Java, Python, and many more. This is the verification methodology of our project. We convert the code to Llvm IR format with Llvm commands. Then by parsing and using API calls, we convert to the bounded model checking formula in SMT-LIB encoding. Lastly, we give that model to a SMT solver for final sync verification. But this semester we are not concerned with how to get optimal input code from Llvm and how to convert a code to Llvm IR format. We will focus that on next semester. Now, methods of conversions and encodings. Scheduling is the behavior of threads in the model. We use explicit scheduling, and that means only one thread can move at a time. Encoding of the store instruction. Store instruction takes two parameters, a source and a target. In SMT-LIB we can just use assignment operation. However, if the store operation is done on a global variable, then p variable means the last store program counter is updated as well as in the example. Here is an example store operation. We have this in Llvm instruction, and then we are converting. First we state the active thread and the program counter of this thread, and then we do the assignment, we update the last store program counters, and finally we update the thread program counters. Now another instruction, branch operation. Branch has two types in Llvm instruction format, conditional or non-conditional. Conditional means if the boolean variable is true, branch to first label, else branch to the second label. Here is an example. Comparison instruction contains four variables: the result, greater or less than, first value to compare, and second value to compare. And here is an example. The compare operation is done, and if, for example, the first value is greater, and then Cmpe1 becomes true, otherwise false. Now assertion. Assertion is the part decides if there is a bug or not in the program. For now, we are just checking if a thread's program counter ever gets the value of fail conditions program count. Some other conversions are bitcast, sign extension, function calls, etc. My results for this semester are actually satisfying because I had two test cases to write my code, and two of them are working correctly. However, we need more test cases to check our program. These are the results. We had two cases, espmc.c and carter.c, and these are the bound values for the verification, and these are the results. Also, compared to other professional verification programs, the results are seen to be correct. As conclusions, we can formally verify programs using SMT and bounded model checking. Also, by using Llvm, verification can be done in many languages. Another advantage is bounded model checking is a guaranteed way to find bugs compared to unit tests. As for next semester's work, we will focus firstly on encoding. Efficient encoding can result in faster verification time. After we have a decent tool, We will try benchmarks in the SV-Comp software verification competition. We are actually considering joining the competition. And lastly, we will try our tool in real-life test cases.